In the next part of the course, we're going to talk about these two cases known as variance known or variance unknown. So this short screencast is going to kind of give you an idea of what that really means. So up until now, we've assumed that we know sigma, which is the population standard deviation. That's different from sample standard deviation, which is lowercase s. Generally, this will never be known with absolute certainty. However, many processes have a long history and sigma is essentially known. So let's say there's been a factory producing a widget for 10 years, and based upon that long history of data, you really know a standard deviation of the population. Also, as n gets big, the sample standard deviation s approaches the population standard deviation sigma. So the previous analysis can be used with large samples. Even if the population standard deviation is unknown, if you have a really big sample, then you can assume that the variance is known. I wanted to kind of demonstrate this with an example. This is a simulation in Excel. I have some true population parameters. I'm just assuming that these are the true population parameters, mu, which is 20, and the variance, which is 2. And I've got up to, I think, 100 different samples. In Excel, I have just randomly chosen through a random number generator. I'm calculating items that follow this distribution. And what I'm doing for each line in this table is I'm taking the average of up to and including that sample. So this third row would be there's 3 samples. The fourth row would be if there's 4 samples. I'm also calculating the variance, the sample variance. Now again, the true parameters are 20 and 2 for the average and standard deviation of the population. And you see that when we have very few samples, up to at least 5 to 10, the sample average and the sample variance in this particular simulation are not matching the true parameters. On the left here, this is the sample average, which goes to the left axis. It approaches 20 when we get up to very large sample size, and the variance also kind of goes back and forth until we're up to a certain sample size. I can go ahead and recalculate, and that updates all of the formulas on this sheet. You can also press F9 if you want. And you see that depending upon the simulation, here's kind of an interesting one. The sample average and sample variance, it takes a long time to actually approach the true population parameters, if at all. So in this one, the average here is approaching a little over 20, and the variance is approaching a little less than 2. So bottom line, if you have few samples down here, then you really don't know the sample variance. Average tends to approach the actual average a lot faster than variance. So with small sample sizes, as I just demonstrated, sigma is not known, so we use the sample standard deviation S along with a new distribution that I'm going to talk about in a subsequent screencast called the T distribution. And this is known as the variance unknown case. And as I noted above, if variance is unknown but n is large, then we can use the normal distribution, and this would be the variance known case. I know this is confusing, so I have a little flowchart here. We start, is the true population variance known? That's what sigma squared is. That's not the sample variance, that's the population variance. If it's known, then we can use the normal distribution as we've done previously. And in this case, we can calculate a z-value, x bar minus mu over sigma divided by root n, or you can use Excel norm.dist function. If the variance is not known, then we can ask ourselves, is n sufficiently large? And some people will say n has to be greater than 75 to 100, but your textbook recommends if n is greater than or equal to about 40. If that's the case, then we're going to also assume that this is the variance known case. Again, in this simulation, when the sample size gets bigger than about 40, our sample variance is getting close to the population variance. However, if the sample size is not greater than 40, then you're going to have to use something known as a T distribution. This is known as the variance unknown case, where we calculate a T statistic, this formula up here. And again, I'll be talking about this in a subsequent screencast. But when we have the variance unknown case, the analysis is a little bit different than the variance known case. This screencast just gives you an introduction to the variance known and the variance unknown cases that we'll be talking about in the future. Thanks for watching.